Everything has its wonders, even darkness and silence. What does our future hold? What does the future of time itself look like? How will the universe meet its end? We may never be truly certain, but science has begun to paint a stunning picture of how the future might unfold. This journey through deep time may look like a simple prediction of what's to come, but it's not what you think, because we're living in an infinitesimally brief window of cosmic history. The universe has only just begun. What we do now, and in the next few years, will profoundly affect the next few thousand years. The only conditions modern humans have ever known are changing, and changing fast. If this cosmic timeline vision wasn't understood, then humanity would miss the profound realization that our actions today shape millennia while we exist in only a fraction of universal time. Nothing stays the same on this planet. Everything changes. The Earth is going into one of these jumps, and you don't know what's going to be on the other side of those jumps. Let's take a journey to the end of time. We will travel through time exponentially, doubling our speed every 5 seconds. The vision of the future will surely evolve as we probe for more clues. But one thing is clear: the universe has only just begun. From the end of the Holocene era to the final black hole evaporation, we'll witness events that stretch beyond human comprehension, revealing the true scale of our cosmic story and the precious, fleeting moment in which life is possible. Before we embark on this mind-bending journey through deep time, make sure to subscribe to the Sleep Lab and hit that notification bell. We explore the most fascinating mysteries of science, space, and the cosmos, content designed to expand your mind and help you drift into wonder. Let's begin our expedition to the end of everything. The Holocene has ended. We stand at the threshold of the Anthropocene Era, where human influence has become the dominant geological force shaping our planet. But as we peer into the future, we must remember that nothing stays the same on this world. Everything changes. The Earth is going into one of these jumps, and you don't know what's going to be on the other side of those jumps. The Earth is always jumping, and things move on this planet. Things are not still. Everything is turning. What unfolds before us is a cascade of transformation that begins almost immediately in cosmic terms. The familiar rhythms of our world, the climate patterns we've known, the ice sheets that have persisted for millennia, the very magnetic field that protects us from space. All of these are about to change in ways that will reshape the face of our planet. We're entering an age where the only constant is change itself, where the stable conditions that allowed human civilization to flourish are giving way to something entirely new. In the coming decades, the effects of human activity continue to ripple through Earth's systems. The carbon dioxide we've pumped into the atmosphere doesn't simply disappear. It persists, driving temperatures higher and triggering feedback loops we're only beginning to understand. The great ice sheets of Greenland and Antarctica, which have stood as frozen monuments for millions of years, begin their inexorable retreat. As they melt, they don't just raise sea levels. They fundamentally alter the planet's rotation, shifting the distribution of mass and changing the very length of our days by microseconds. But human influence is just the beginning of this story. Moving forward through the centuries, we encounter the first of Earth's great natural upheavals, the magnetic field reversal. Every few 100,000 years, our planet's magnetic poles flip, and we're overdue for this cosmic reset. The process doesn't happen overnight. It unfolds over centuries, during which time our protective magnetic shield weakens and becomes chaotic. Compasses spin wildly, and the aurora borealis dances across skies far from the polar regions. Most dramatically, our technology-dependent civilization faces unprecedented challenges as increased radiation from space interferes with satellites, power grids, and communication systems. As we accelerate through the millennia, the pace of change becomes breathtaking. Comet Hale-Bopp returns to grace our skies once again, a celestial timekeeper marking the passage of 4,000 years. But by then, the Earth below bears little resemblance to the world we know today. Drastic sea level rise has redrawn the coastlines, swallowing entire nations and creating new inland seas. The familiar outlines of continents become memory as the oceans claim their territory. Cities that once stood proudly by harbors now rest beneath fathoms of water, their ruins becoming artificial reefs in a dramatically transformed marine ecosystem. The asteroid impacts begin in earnest, not the civilization-ending monsters of Hollywood imagination, but the steady bombardment that has always characterized our planet's relationship with space. A 30-meter asteroid screams through our atmosphere and explodes over a major metropolitan area with the force of hundreds of nuclear weapons. The immediate devastation is catastrophic, but life, as it always has, finds a way to recover and adapt. These cosmic encounters serve as violent reminders that Earth exists in a dynamic, dangerous universe where extinction-level events are not matters of if, but when. As we push deeper into deep time, the stars themselves begin their slow dance of change. Antares, the red supergiant that has dominated the constellation Scorpius for millions of years, finally reaches the end of its stellar life. The explosion that follows is visible during daylight hours for weeks, casting an eerie red glow across Earth's sky and briefly outshining every other star in the heavens. The shock wave from this cosmic detonation, traveling at a significant fraction of light speed, eventually reaches our solar system, though by then it is weakened to levels that merely create spectacular aurora displays rather than sterilizing all life. The climate system continues its relentless transformation. The Sahara Desert, that vast expanse of sand and rock that has defined North Africa for millennia, undergoes one of its periodic reversals and becomes a tropical paradise. This isn't science fiction. It's happened before, and it will happen again. The shifting patterns of Earth's orbit and axial tilt, known as Milankovitch cycles, gradually alter the distribution of sunlight across our planet's surface. What is now barren wasteland becomes a lush garden supporting vast forests and meandering rivers, while other regions that currently enjoy temperate climates become arid wastelands. Our journey accelerates, and we witness Voyager Witt, humanity's most distant ambassador, finally encountering another star system. This little probe, launched in the distant past of the 21st century, has become an interstellar artifact, carrying messages from a species that may no longer exist in recognizable form. Its encounter with an alien star system represents one of humanity's greatest achievements, the first human-made object to traverse the vast gulf between stars. Yet by the time this historic moment occurs, Earth itself has changed so dramatically that the civilization that launched Voyager would be as alien to its inhabitants as any extraterrestrial life form. The interglacial period that has blessed human civilization for the past 10,000 years finally comes to an end. The ice sheets that have been retreating begin their advance once again, grinding southward with inexorable force. The great cities of Northern Europe and North America disappear beneath kilometers of ice, while the climate patterns that support agriculture shift dramatically toward the equator. This isn't global warming reversed. It's part of the natural rhythm that has governed Earth's climate for millions of years, a reminder that our planet's systems operate on timescales that dwarf human history. Supervolcanoes, those sleeping giants that have shaped Earth's destiny throughout geological time, stir to life. The Yellowstone caldera, which has been building pressure for hundreds of thousands of years, finally releases its fury in an eruption that makes historical volcanic events seem like gentle sighs. The explosion ejects so much material into the atmosphere that it briefly blocks out the sun, triggering a volcanic winter that lasts for years. Ash falls like snow across continents, and the global food chain collapses as photosynthesis becomes impossible under the darkened skies. Yet even this planetary catastrophe becomes just another chapter in Earth's long story of destruction and renewal. New land masses rise from the ocean depths. A new Hawaiian island appears as the volcanic hotspot that created the entire island chain continues its patient work of building mountains from the seafloor. These fresh lands, born from fire and emerging into sunlight for the first time, represent hope and renewal in a world of constant change. They will become home to new ecosystems, shaped by whatever species manage to reach their shores and adapt to their unique conditions. Entire island chains emerge from the depths as tectonic forces reshape the ocean floor. The slow, relentless drift of continents continues its ancient dance, measured in centimeters per year, but inexorable over geological time. The Pacific Ocean, which has been shrinking for millions of years, continues to close as the continents surrounding it drift inexorably together. The Atlantic, conversely, grows wider as the mid-ocean ridge continues to produce new seafloor, pushing the Americas ever farther from Europe and Africa. Human artifacts begin their inevitable surrender to time. The Apollo footprints on the Moon, those first tentative steps of a species reaching beyond its homeworld, gradually fade under the constant bombardment of micrometeorites and solar radiation. Without an atmosphere to protect them, these symbols of human achievement slowly erode away, grain by grain, until nothing remains but the faintest depression in the lunar dust. It's a poignant reminder that even our greatest accomplishments are temporary against the vast scales of cosmic time. Betelgeuse, that familiar red giant marking Orion's shoulder, finally exhausts its nuclear fuel and explodes in a spectacular supernova. For months, this stellar death illuminates Earth's sky so brightly that people can read by its light at midnight. The explosion marks the end of a star that has been visible to every human civilization, a constant presence in our night sky that suddenly blazes forth and then disappears forever, leaving behind either a neutron star or a black hole as its final legacy. Stone monuments, those enduring testaments to human creativity and ambition, finally succumb to the patient work of erosion. The pyramids, Stonehenge, Mount Rushmore, all the markers our species has left to proclaim its existence, slowly crumble under the assault of wind, water, and chemical weathering. What took years or decades to build requires millions of years to completely erase, but time is patient, and nature always wins in the end. The cosmic hazards intensify. A deadly gamma ray burst from a distant galaxy sweeps across our solar system, bathing Earth in lethal radiation. These cosmic lighthouses, the death cries of massive stars in distant galaxies, can sterilize planets thousands of light years away. If Earth happens to lie in the path of one of these cosmic beams, the ozone layer vanishes in hours, and the surface becomes uninhabitable for any complex life forms. It's a stark reminder that our planet's fate is tied not just to local conditions, but to events occurring in the furthest reaches of the universe. Mars's moons, those tiny, irregularly shaped remnants of ancient impacts, finally meet their destiny. Phobos, spiraling ever closer to the red planet due to tidal forces, eventually crosses the Roche limit and disintegrates, forming a spectacular ring system around Mars. For a brief period in cosmic terms, our planetary neighbor becomes a ringed world, a magnificent sight for any observers who might exist to witness it. Saturn's rings, those iconic bands that have graced the gas giant for millions of years, finally spiral down into the planet's atmosphere. These icy particles, some as small as dust grains and others as large as houses, gradually lose orbital energy and rain down onto Saturn's cloud tops. The planet that has defined beauty in our solar system for so long becomes just another bland gas giant, its defining characteristic erased by the inexorable workings of orbital mechanics. Antarctica, that vast frozen continent at the bottom of the world, finally surrenders its ice to the warming climate. The last ice sheet melts away, revealing a landscape that has been hidden for millions of years. Mountains emerge from beneath kilometers of ice, and new seas flood the valleys between them. The global sea level rise from this final melting event drowns the last remnants of coastal civilization, creating an entirely new world map where ocean covers land that has been dry for millions of years. The ultimate terrestrial catastrophe arrives in the form of a major asteroid impact. Unlike the smaller objects that have peppered Earth throughout this journey, this visitor is large enough to threaten all complex life. The impact creates a crater hundreds of kilometers across and throws so much debris into the atmosphere that the climate shifts dramatically. Nuclear winter conditions persist for years, and the food chain collapses from the bottom up. Yet even this seemingly terminal event becomes just another reset button in Earth's long history, clearing the stage for new forms of life to evolve and flourish. As this first segment of our journey concludes, we witness the formation of a new supercontinent. The slow drift of tectonic plates, continuing its patient work across hundreds of millions of years, finally brings the scattered continents together once again. All the land masses that have been separated by vast oceans merge into a single, massive continent surrounded by a global ocean. This new Pangea becomes a laboratory for evolution, where species that have been isolated for hundreds of millions of years suddenly find themselves neighbors once again. Through it all, the sun continues to shine, but it too is changing. Even our seemingly constant star is evolving, gradually increasing its luminosity as nuclear fusion in its core becomes more efficient. This subtle brightening, imperceptible from year to year, but significant over geological time, begins to drive Earth's climate toward a new phase of its long history. The stage is set for even more dramatic changes as we continue our journey toward the end of time, when our star itself will become the agent of Earth's final transformation. Now, we are moving to the second part of the documentary, in which we talk about the death of the sun and the transformation of the solar system. For eons, the sun shone as the unwavering center of our existence. Its steady light-shaped continents nurtured life and marked time for everything that lived and evolved in its orbit. Yet what seems eternal from the perspective of human history is, in cosmic terms, ephemeral. No star, not even our own, burns forever. In this segment, we unlock the secrets of the sun's life, its beautiful demise, and the final fate this sets into motion for Earth and the entire solar neighborhood. As we step forward in time, the clock begins to run faster, centuries passing in a heartbeat. The sun's current tranquil brilliance is just the middle act of its story. Every second, deep within its core, nuclear fusion transforms over 600 million tons of hydrogen into helium. For billions of years, this engine has kept the star stable, pushing outward against gravity's constant crush. The heat and light generated by this process have made Earth a cradle for oceans, forests, and civilizations to bloom. But fusion is a finite resource. Gradually, the supply of hydrogen dwindles. The sun's core, layered now with helium ash, contracts under gravity, growing hotter and denser. The surrounding layers respond by fusing hydrogen even faster, and this uptick in activity isn't benign. The sun's energy output starts to inch upward, slowly at first, then inevitably. This increase is so subtle that no living creature could ever detect it. But over millions of years, it becomes decisive. Earth, once shielded by a precarious balance, is caught in this mounting furnace. As the sun grows about 10% brighter every billion years, even slight changes send ripples through our planet's climate systems. The result is not a gentle warming, but relentless, runaway greenhouse effects. Oceans warm and evaporate. Water vapor, itself a powerful greenhouse gas, thickens the atmosphere. A tipping point is crossed. More heat gets trapped, which in turn vaporizes yet more water, amplifying the spiral. The process accelerates, and the once blue planet leans toward suffocation. The biosphere, as diverse and resilient as it is, cannot stave off the inevitable. Higher temperatures force plants to close their stomata, the microscopic pores in their leaves, to conserve water. In doing so, they starve themselves of carbon dioxide, halting the miracle of photosynthesis that has fueled life for billions of years. As plants wither, the ripple effect runs through every living chain. Herbivores cannot survive without vegetation, and carnivores follow as ecosystems unravel. Atmospheric oxygen, never replenished by plant life, fades. In the mounting heat, even hardy, adaptable microorganisms struggle to persist in scattered refuges. With the planet's lungs collapsed and its seas turning to mist, the Earth begins a slow march towards sterilization. Eventually, surface temperatures soar past the boiling point for liquid water. The oceans, for hundreds of millions of years the birthplace of life, start to boil away into space. The vapor rises high, split by solar radiation into hydrogen and oxygen. The hydrogen, so light, escapes into the void, never to return. The Earth, lush and vital for so long, transforms into a barren, scorched wasteland. But the sun's death has only just begun. As more hydrogen fuel is exhausted, a new process takes over. With its core, now composed chiefly of helium, the internal heat is no longer sufficient to fuse these new elements. Not yet. Gravity wins for a time, crushing the core inward and raising the temperature even higher. Suddenly, the sun undergoes a crisis. Temperatures in the core soar past the threshold needed to fuse helium. The transition is anything but smooth. With a massive, almost explosive burst, helium ignition sets off a rapid expansion. The sun's outer layers swell outward, its volume growing hundreds of times larger. The surface cools as it expands, taking on a ruddy, menacing glow, visible from the most distant planets. the sun has become a red giant. From Earth's perspective, if anything survives to see it, the sky grows ever stranger. The sun dominates the heavens, sometimes appearing so vast it seems to fill a third or more of the sky. Its light has shifted spectrum, bathing everything in crimson and omens of doom. The pace of change is shocking now. What took billions of years before now happens in tens or hundreds of millions. The inner planets draw closer to the sun's monstrous surface as the star loses mass and its grip on the solar system weakens. Mercury, closest to the sun, spirals inward and is engulfed outright. Venus is next, meeting the same fiery fate. The fate of Earth is more complex. As the sun swells, it also blows off enormous amounts of stellar wind, shedding much of its substance into the surrounding system. This reduces its gravitational hold. There is a small chance that Earth's orbit drifts outward just enough to escape direct engulfment. But if the calculations tip the other way, and most do, the swelling atmosphere will swallow, burn, and vaporize the planet entirely. In some tellings, Earth may escape actual consumption, living on as a charred, airless cinder. If so, this will be a brief, bitter reprieve. The unrelenting heat will strip the world of any remaining traces of life, melt the very crust, and erase continents under lava seas. For practical purposes, the planet is dead. Its billions of years of geology, biology, and memory reduced to drifting dust. Meanwhile, the rest of the solar system is not spared. Mars might survive as a frozen exile, its landscape cooked but not consumed, while the outer worlds, gas giants like Jupiter and Saturn, stand at a greater distance, watching their own satellite systems evaporate and decay. Icy moons lose their atmospheres, inland seas boil off, and asteroid belts drift further from their original formation. The entire solar system, once organized and alive, becomes a realm of ruins orbiting a dying sun. The red giant phase of the sun is surprisingly short-lived, especially when measured against the slow passage of its earlier main sequence. Within another billion years or so, the core, having burned through its helium stockpile, contracts once more. Critically, the star does not have enough mass to fuse the carbon and oxygen now piling up in the core. Unable to ignite another stage of burning, the sun's fate is now inevitable. With energy dropping off, the sun's outer layers are gently shrugged off by stellar winds, forming a stunning glowing shell, a planetary nebula, the briefest and most beautiful of astronomical phenomena. At the center, all that remains is the sun's hot, dense core, a white dwarf. This stellar corpse is roughly Earth-sized, but contains much of the sun's former mass. It glows not from fusion, but from residual heat, fading over countless eons. Where there was once a system of 9 complex, dynamic planets orbiting a brilliant yellow star, there is now only a collection of icy remnants and naked rocks circling a dim ember. The white dwarf sun, while intensely dense and hot at first, will cool and fade over trillions of years, ultimately becoming a cold, dark, and invisible black dwarf, the last physical memory of a once mighty solar furnace. Across the Milky Way, and indeed the cosmos, this fate is not unique. Every star of modest size, like our sun, will travel this same path from fusion powerhouse to white dwarf to cold cinder. Brighter and larger stars blaze hotter and die more violently, exploding as supernovae and sometimes leaving behind neutron stars or even black holes. But the majority of stars, including the ones that probably nurtured most life, end in silence, cooling slowly, orphaned from the fire that once sustained them. With the sun's light gone, the solar system enters a new, timeless darkness. Gravitational forces remain, but with most energy and structure lost, the remaining bodies are subject to cosmic accidents. Some may be kicked out of orbit to wander forever in interstellar space. Others are dragged into the white dwarf or collide with each other in a mute ballet of entropy. The memory of the solar system, its planets, moons, and the stories of life, is now only preserved as a ghostly dance of relics among the stars. The story echoes out across the entire universe. One by one, even the smallest stars, red dwarfs, some burning for trillions of years, finally exhaust their own stores. As they go dark, no new stars form to replace them. There is no more raw hydrogen in the star nurseries of the galaxy. The process of star birth has ended for good. The sky, which for eons glittered with countless suns, turns forever black. Darkness truly claims the cosmos. Some enthusiasts might look to rare phenomena for hope, perhaps a freak collision between massive brown dwarfs or runaway neutron stars might spark a brief, brilliant resurrection. An accidental supernova, a single burst of starlight in an otherwise pitch-black universe. But these events are fleeting, and with every passing eon, the sky grows quieter. All this, the grand drama of stars, planets, and light, plays out well before the universe even reaches a fraction of its total lifespan. In mere cosmic adolescence, the last sun dies, the last planet freezes or vaporizes, and our local narrative falls silent. What remains is the beginning of the next chapter, the age of stellar remnants, degenerate matter, and a starlit universe fading into the background hum of time. This is the end of the solar age, a finale both grand and universal. For every world born in the warmth of a star, this fate is written in the laws of physics. The universe's great experiment with light draws to a close, not with one cataclysmic destruction, but with the slow extinguishing of everything bright. The death of the sun is not just the closing of one era, but the quiet overture to deeper changes in the cosmos itself. Now, we are moving to the third part of the documentary, in which we talk about the Degenerate Era, the long, silent afterlife of stars, and the transformation of the universe as darkness claims the cosmos. For billions of years, stars have burned in the night, forging the elements of life in their cores, illuminating galaxies, and giving rise to worlds like our own. But even stars cannot burn forever. In the immensity of time after the last sun flickers out, existence enters a new epoch, the Degenerate Era. In this profound, eerie age, the universe is strewn with the cold remnants of what once was. White dwarfs cooling in solitude, neutron stars spinning with fading energy, and black holes lurking silent and ever hungry. Gone are the days of warmth and light. This is a cosmos of ghosts, relics, and possibilities almost beyond imagination. In the beginning of the Degenerate Era, remnants of the former age still linger. The white dwarfs, like our own sun after its fiery death, continue to cool. But their faint glow is all that punctuates the black, cold void stretching between the galaxies. These stellar husks, packed into spheres no larger than Earth, are so dense that a teaspoon of their matter weighs as much as a mountain. They once shone with the afterheat of fusion, but now that heat steadily escapes into space, and their light quiets, ever dimmer, ever colder. Across the cosmos, stars have ceased to be born. The hydrogen reserves that once filled nebulae and gave rise to new suns have been exhausted or driven away by ancient supernovas. What remains are the leftovers, the white dwarfs, neutron stars, brown dwarfs, and black holes, all drifting further into the cold distance as time marches relentlessly forward. Imagine a galaxy of the future. Once busy with new stars forming and old stars dying, it is now a cemetery, silent save for a few chance encounters of the leftovers. Where star nurseries once twinkled, there stretched only shadows, the vacuum broken by the occasional lonely wanderer. Gravity, never ceasing its patient work, slowly ejects dead stars and planets from their native galaxies, flinging them into the freezing dark between galactic clusters. Every so often, against the silence, something extraordinary happens. Two stellar remnants collide. A brown dwarf, a failed star never bright enough to ignite fusion, drifts close to another, and together they merge. Their combined mass may be enough for a brief and improbable moment to spark new fusion, a flicker of starlight rekindled in the cosmic night. Or perhaps two neutron stars meet after eons, their fantastic energies combining in a supernova brighter than any since the dawn of stars. These events are rare, flashes against the near-eternal darkness, but they remind us that the drama of the universe is not quite finished. Still, such moments are the exception. The future belongs to the cold, the collapsed, and the degenerate. White dwarfs, as they cool, pass into blackness, what astrophysicists call black dwarfs. These are objects so cold and so dark they are, for all practical purposes, invisible. Dense cinders of stars, their internal atoms crushed to 1,000,000 times the density of our sun, yet radiating almost no energy. The processes that would finally bring about the first true black dwarfs in the universe take time, a span so vast there are almost certainly none yet in existence. In this unimaginable future, however, these perfectly dark, cold objects will fill the universe. Over the course of trillions of years, these black dwarfs will decay further, their quantum mechanical energy leaking away through processes like proton decay, if indeed protons are not truly forever. Current theories suggest protons, building blocks of the atoms making up everything in the material universe, might one day simply perish. If this is true, the matter making up the last stars will eventually evaporate away, vanishing into the void as faint radiation. If proton decay does not occur, these objects might persist almost endlessly, the last remains of anything solid in the universe. Even so, the universe is not entirely without drama. In the darkness, black holes, the ultimate result of gravity's inexorable pull, continue to dominate their domains. Most matter that doesn't escape a galaxy, over trillions upon trillions of years, is likely to be subsumed into supermassive black holes at galactic centers. As time goes on, these monsters become the main gravitational anchors of the cosmos, and as more errant material drifts close, black holes grow still larger. Sometimes, black holes collide, merging into even more titanic singularities. Each of these cosmic collisions sends gravitational waves rippling across the universe, a faint drumbeat echoing through otherwise endless silence. Yet even for black holes, there is no eternal dominion. According to Stephen Hawking's groundbreaking work in theoretical physics, even the mightiest black hole slowly evaporates through a process called Hawking radiation. At the quantum level, space is filled with virtual particles flickering into and out of existence. Near the event horizon, the invisible boundary from which nothing can return, sometimes one particle of a quantum pair falls in, while the other escapes. To an observer far away, it appears as though the black hole is emitting radiation, For small black holes, this process is rapid, but for the titans formed from whole galaxies, it takes longer than any span we've discussed yet, upwards of 10 to the 100 years. During the Degenerate Era, some theorists have speculated that any surviving life forms might seek refuge around cooling white dwarfs, eking out an existence in a universe that has grown hostile to complexity. Perhaps civilizations, forced to ration their energy, change their very tempo. Imagine beings for whom a single thought might take trillions of years, whose societies rise and fall on a timescale that would be imperceptible to us. In such a night, life could, for a while, persist, strange and slow, but aware nonetheless. Or perhaps, after the collapse of everything, some random quantum fluctuation could seed a brief, ephemeral return of sentience, a little island of intelligence in the endless dark. Time itself grows strange in this era. With the death of the last sun, the age of starlight comes to an end, and temperature across the universe plummets almost to absolute zero. The lights that illuminated the universe during its middle age are extinguished, and so too is the brief window in which life, as we know it, is possible. To comprehend the fleeting opportunity for existence, consider this. As a fraction of the universe's lifespan, the time during which life is possible is astonishingly small. 1,000th of a billionth of a percent. The universe's adolescence, so bright and brief, is now over. The future unfolds in the dark. Galaxies, those grand islands of stars, become the homes of black holes and black dwarfs. Over time, even black holes, the last bastions of mass and energy, begin to evaporate, glowing faintly as they emit Hawking radiation. As they disappear, they further erase any remaining large-scale structure from the cosmos. In this era, even gravity, which has shaped so much of the universe's fate, finally loosens its grip. Eventually, galaxies themselves become mere shells of their former selves, populated only by relics drifting in the endless black. The distances between objects expand as the universe itself is driven apart by a mysterious force, dark energy. This energy, inherent even in empty space, propels galaxies away from each other at ever-increasing speeds. Before long, the light from distant galaxies will be globally redshifted so much that it becomes undetectable, effectively erasing our ability to ever observe the broader universe. The secrets of the cosmos are locked away forever. During this time, anywhere matter survives, perhaps inside black dwarfs, or bound tightly within ultimate stellar remnants, it continues to decay. If proton decay is a reality, even the atoms themselves will not last. Material objects, from dead stars to isolated particles, will transform into fleeting flashes of radiation. If proton decay is forbidden, these remnants persist. But even then, rare events such as quantum tunneling might disrupt the apparent stability of these objects, causing their gradual dissolution. And so, what was once a universe vibrant with life, dominated by suns, and teeming with possibility, is reduced to a thin and bleak skeleton, a cosmic boneyard. The final stars have faded. The galaxies are graveyards of invisible corpses. The universe is littered with black dwarfs, neutron stars, and sleeping black holes. Even the mighty are silent here, and the only remaining events, rare and gentle, are the slow decay and collision of these ancient remnants. In this lonely epoch, time seems almost to stand still. On the vast scale of the universe, ages may pass between meaningful events. No new light will ever be born. Energy is now spread so thinly that no new structure or complexity can emerge. The story of creation is now a memory scattered across cold, receding space. The Degenerate Era is a story not of fiery cataclysms or cosmic birth, but of the ultimate patience of the cosmos, a waiting, endless and silent, in which what once was gradually fades away. For those who contemplate these ultimate times, it is both a warning about the impermanence of all things and a cause for wonder. Everything we know, everything possible, is only a brief moment in the immeasurable life of the universe. And though the story has grown dark and cold, there remains a strange beauty in the contemplation of this future. For as Helen Keller once said, everything has its wonders, even darkness and silence. The universe has entered the next phase of its existence, its vibrant youth and starlit adolescence only a memory kept within the blackened cinders and silent drums of space, waiting as the arrow of time carries us ever deeper into the unknown. Now we are moving to the fourth part of the documentary, in which we talk about the black hole era, a time governed by gravity's ultimate power, Hawking radiation, and the silent evaporation of the universe's last great titans. After the end of ordinary stars and the fading out of white dwarfs and neutron stars, the universe finds itself a place ruled by black holes. These are not simply the remnants of massive suns, but cosmic monsters grown immense through the slow cannibalization of everything left behind. Galaxies, drifting dead matter, stray comets, and the debris of countless previous cosmic events. As the universe enters the black hole era, even the concept of time begins to stretch toward absurdity. Each moment now spans longer than the age of our observable universe, cosmic seconds which last trillions upon trillions of years. Black holes are strange creatures. Born from the deaths of massive stars or the collision of dense stellar remnants, they are formed when matter collapses under the force of its own gravity, compressing into an infinitely tiny, infinitely dense point called a singularity, surrounded by the event horizon, the boundary from which nothing, not even light, can escape. For countless trillions of years into the future, black holes serve as nature's ultimate trash compactors, swallowing all matter and energy that comes too close. In this phase, the supermassive black holes at the centers of galaxies become key players. These behemoths, some of them billions or even trillions of times more massive than our sun, continue to merge and grow. Over unimaginable spans of time, even small black holes are shepherded toward these galactic monsters, drawn together by the last vestiges of gravity. Occasionally, these mergers trigger cosmic fireworks. As two black holes spiral into each other, they twist space-time itself, sending out mighty ripples called gravitational waves. These waves, which travel at the speed of light, are space-time's deep solemn tones, the last music the universe will ever know. To imagine this, think of two black holes locked in their death spiral. They circle each other at dazzling speeds, space itself flexing and ringing with each orbit. When they finally collide, their event horizons fuse in a fraction of a second, and space rings with gravitational waves propagating out into the cosmos. If you were to be close, though in reality, nothing could survive so near, you would feel the fabric of reality itself stretch and squeeze, a silent, mighty resonance. But the universe is nearly empty now. The grand galaxies of earlier ages have largely dispersed. Material left over from previous epochs, dead stars, and other black holes have all been drawn in or ejected into lonely intergalactic space. What remains are zombie galaxies, vast, dark structures consisting mainly of black holes with occasional rogue degenerate remnants. Time has slowed so much that the universe can go ages with nothing but the faint rumble of black hole mergers breaking the silence. For a long while, black holes seem indestructible. Their extreme gravity traps everything, and for much of the universe's history, they were considered the final rest for any and all matter. But then quantum mechanics comes into play, revealing that even these apparent prisons are not truly eternal. In the 1970s, Stephen Hawking proposed that black holes are not perfectly black. The quantum vacuum surrounding them churns with virtual particles. For a fleeting instant, pairs of particles and antiparticles come into existence and almost immediately annihilate one another. Near a black hole's event horizon, this process can split pairs apart. If one falls in and the other escapes, to an outside observer, the black hole emits a tiny amount of radiation, now known as Hawking radiation. This process of slow leakage takes incomprehensible time spans to have any observable effect, especially for massive black holes. Stellar mass black holes may last 10 to the 66th years or more, while supermassive black holes at galaxy centers can survive for up to 10 to the 100th years. But as the eons flow by, the cosmic ledger keeps ticking down. Black holes gradually lose mass, shrink, and finally, after spending most of the universe's unimaginably long life, approach their end. When black holes finally draw to their last moments, the process accelerates. As the remaining mass diminishes, Hawking radiation rapidly grows more energetic and intense. In their final instant, black holes emit a burst of high-energy particles and radiation, briefly lighting up the darkness one last time before fading completely and leaving no trace. This is time's ultimate eraser. Even the records of what a black hole once devoured, once inscribed on its event horizon as information, now seem to be lost forever. At this point, nearly all large-scale structures that the universe once knew are gone. Black holes, final architects of cosmic order, have vanished, leaving a universe that is cold, dark, and almost featureless. The remaining constituents of the cosmos are mostly low energy, long wavelength photons, heat, radiation, and the lightest, most elusive subatomic particles, drifting ever farther apart as the fabric of space stretches under the influence of a mysterious force, dark energy. Dark energy is not matter, nor is it ordinary radiation. Its nature is still one of the great scientific mysteries, but we know its effect all too well. It causes the universe to expand at an ever-increasing rate, pushing galaxies and all matter still further and further apart. Even before the last black holes are gone, distant objects recede so quickly that their light is stretched beyond detectability. They disappear, not because they no longer exist, but because the universe itself has pulled them beyond our cosmic horizon. The observable universe becomes emptier, colder, more alone, and as black holes die out, and the universe continues to expand, another frontier arises. Physicists have asked, will the universe die in fire, or in ice? The evidence now points toward ice. There will be no final cataclysm, no all-consuming fiery burst, but instead an endless drift into chill and darkness. In the words of poets, the world will end not in fire, but in ice, deep, utter cold, and stillness. Why does this cosmic freezing occur? Because energy itself, as the universe expands, gets spread more thinly across space. In every cubic centimeter, there is now less and less energy, and nothing new can ever be built. the temperature of the cosmos approaches absolute zero, and all physical processes wither away. The last living systems, if any existed, would have been gone long before. For the remainder of existence, the universe is an infinite blank, silent, black, and almost perfectly cold. But some mysteries, even now, remain. Physicists study the nature of dark energy and propose that its dominance may not last forever. If it weakens over time, the universe might one day reverse its expansion and collapse in a cataclysmic Big Crunch. Or perhaps dark energy could strengthen, tearing even atomic bonds apart, the so-called Big Rip. Yet the most accepted theory is an endlessly accelerating universe, rushing outwards faster and faster as its destiny unfolds. The black hole era is not just an era of endings. In the unthinkably far future, some have speculated about bizarre quantum events, a new universe budding out of the cold, or a sudden fluctuation exploding spontaneously with fresh energy. Such ideas remain speculative, but they show the possible strangeness inherent in a cosmos where nothing is forbidden by time or quantum. Mechanics only rendered rare and distant by the weight. For us, the black hole era is a kind of cosmic coda, a tale of the patience and slow unraveling of creation. It is a time during which the remaining traces of complexity, structure, even memory itself, are erased by the deep forces of entropy. This is not a time of drama as we know it, but a slow fade out, a music that becomes quieter and quieter until only silence remains. If we could observe the universe at this late stage, what would we see? There might remain some song, the faint, final ringing of space-time itself, as the last black hole in the cosmos dies and the last gravitational waves ripple out. Then utter darkness and utter quiet. The story that began with a bang ends in a whisper, a universe where even time itself seems to become meaningless. The black hole era is thus the universe's grand finale. The last hope of matter to resist decay is gone. The last giants of gravity are dispersed into an evaporation that is truly final. All that is left is the infinite cold expansion, a cosmos waiting with no witness, no structure, and nothing left to change. And so, we leave the black hole era behind, journeying toward the final curtain, a future even more strange and simple, where the difference between past, present, and future is lost, and where the last embers of the cosmic fire finally, at last, go out. Now we are moving to the last part of the documentary, in which we talk about heat death and new beginnings, the final fate of our universe, the role of dark energy and entropy, and the most profound speculations about what, if anything, comes after the end. After the last black hole evaporates, the universe, once rich and bright, finally surrenders to a fate that has been foreseen in equations and glimpsed in the silence between the stars. This is the era where history, creation, and transformation have all come to rest. It is an epic so vast that even words begin to fail, for time itself seems to stretch and slow, and at last to lose all meaning. The black hole era has ended. There are no more stars, no more planets, no more atoms, only the faint afterglow of particles of light and a gentle hiss of subatomic decay. Darkness now reigns across the whole cosmos, but even now, the universe is not yet done transforming. At this cosmic horizon, we enter an age dominated by the most elusive and implacable force known to physicists, dark energy. Empty space, as it turns out, is not truly empty. It is filled with a peculiar form of energy that exerts a pressure, a repulsive force, causing the fabric of the universe to expand at an ever-increasing rate. Our cosmos, which was once dominated by matter and radiation, now finds itself governed by dark energy and the slow, silent progress of entropy. Galaxies, already dark and empty, drift away from each other faster and faster, receding into unreachable isolation. As space continues to stretch, every remaining particle of light is literally pulled apart, its wavelength elongated, its energy drained. The universe cools inexorably, heading towards absolute zero. In this frozen future, the second law of thermodynamics achieves its ultimate victory. All useful energy is spread out so thinly that nothing more can ever happen. There are no more temperature gradients, no more flows of energy, no more chemical reactions. The universe enters a state of maximal entropy, perfect disorder, perfect uniformity, perfect silence. Time becomes meaningless. Philosophers and poets once wondered, will the world end in fire or ice? The fate that physics now predicts for the universe is a death in ice. An ever colder, ever emptier cosmos, where even the very fabric of reality itself seems devoid of happening. As trillions upon trillions of years tick by, the temperature of everything approaches the cosmic microwave background. The ghostly echo of the Big Bang Bang, only infinitesimally above absolute zero. Everything that once was is gone. The story of stars, planets, and life recedes into the most distant of memories. In this darkness, even the idea of time erodes, for nothing ever changes. There are no clocks, no cycles, no events by which to measure the passage of moments. For the first time, the universe is truly permanent and unchanging. Time becomes meaningless. That phrase echoes through this final epoch, not just as a statement of science, but as a kind of cosmic mantra. The arrow of time, which governed life, work, and growth, is meaningless in a universe where entropy cannot increase further, and there is simply nothing left to do. But before we reach this absolute quietude, some last transformations may occur. For a long time, physicists assumed that protons, the fundamental constituents of atoms, would never decay. But current theories suggest that even protons, given sufficient time, may break down through a process so rare that a single proton might last 100 quintillion years or more. Yet with enough time, this too is inevitable. As protons decay, so does the very last of all matter in the universe. Black dwarfs, if any persist, gradually evaporate, their matter converted at last to the thinnest possible radiation. The memory of atoms, once the bricks of existence, now evaporates into nothing but faint wisps, vanishing into the void. The matter inside the very last black dwarfs, the final traces of the last stars, will eventually be carried away into the emptiness as radiation, gone forever. What remains is a thin, dilute sea of photons, and the lightest subatomic particles scattered so widely across space that the chance of any two interacting is effectively zero. Once the very last remnants of the very last stars have finally decayed away to nothing, and everything reaches the same temperature, the story of the universe finally comes to an end, at least as far as we currently understand. Yet, with so much about the cosmos unexplained, could the universe truly end in final, absolute silence? Or is this bleak future simply the edge of our knowledge, a shadow cast by our limitations? One possibility lies in the nature of dark energy. If dark energy is not truly constant, if it changes in strength or even reverses, our predictions could shift dramatically. Should it weaken over unimaginable ages, gravity may once again dominate, causing the universe to collapse in on itself in a reversal of the Big Bang. the Big Crunch. In this fiery, catastrophic end, every structure, every remnant, and every photon rushes inward and is consumed by unimaginable temperatures and densities. All that existed is compressed into a single point, perhaps setting the stage for a new universe to be born. But what if dark energy strengthens with time? The acceleration could grow so intense that it tears the universe apart at every scale. First galaxies, then stars, planets, and even atoms themselves are rent asunder in the so-called Big Rip. In this bizarre ending, nothing survives. Not even space and time themselves would persist as we know them. Even more intriguing is the possibility that the multiverse, an endless expanse of alternate universes, each with its own laws of physics, might exist. Perhaps our universe is one in a limitless sea, some dying in silence, others torn apart, others still giving rise to new forms of life and creation inconceivably different from our own. Some regions might host the right conditions for life, while others could collapse or be destroyed prematurely. Each could bear witness to its own unique fate. Speculation about the multiverse opens unimaginable vistas. Could life escape the finality of its own universe? If so, what kind of technology, energy, or intelligence would be required? We imagine impossibly advanced civilizations attempting to forge a way out, whether by creating a simulated or virtual universe to shelter in, or, with technology beyond our understanding, by constructing a new universe entirely, a so-called baby universe. This dramatic idea is rooted in speculative theoretical physics, but it stands as a testament to our imagination. Perhaps the end of one universe can seed the beginning of another. Mathematics points toward possibilities stranger still. The equations of quantum mechanics and general relativity may allow, under extreme energy conditions, like those in the collapse of a massive star or an atom smasher of incredible power, a patch of space-time to bud off and form a new, disconnected cosmos. Maybe, just maybe, this is how universes reproduce, not with certainty or regularity, but as an outcome of chance, energy, and cosmic evolution. As we draw ever closer to the true end, philosophically and scientifically, one truth remains. Everything we know is temporary, a fleeting phenomenon in an ocean of time and space. The story of the universe is the story of entropy. And entropy's story is one of endless increase, of order giving way to disorder, of each new structure carrying within it the seeds of its own decay. Yet, within that window, so brief, so vanishingly narrow in the scale of cosmic history, life emerges. Our universe gives life only a brief moment to shine, a haven in time, safe from its fiery birth and icy death. For all life, for intelligence, for reflection, this opportunity is precious, unique, and finite. Measured across the entire lifespan of the universe, life, as we know it, is only possible for an infinitesimal fraction. For every 10 to the 84th power, 1 followed by 84 zeros, parts of the universe's age, the window for life is only a blink. That perspective humbles and inspires. It reminds us to seek knowledge, to cherish experience, and to marvel at the strangeness of existence. The arrow of time creates a bright window in the universe's adolescence, during which life, memory, and history are possible. But it's a window that does not stay open for long. And while our minds turn naturally to endings, the story of the cosmos is fundamentally one of transformation and wonder. As we reach this outermost horizon of thought, We must ask, could the final end itself be a prelude somehow to something new? Do the ashes of one universe seed the birth of another? If nature abhors a vacuum, could some, as yet undiscovered physics allow the cosmic story to continue in a new form? Some speculate that universes with conditions suitable for life might evolve to produce baby universes, launching them as lifeboats to escape their own heat death. Maybe the ability to create new cosmic realms is the final, mysterious function of intelligence and life. The survival of the fittest might take place not just among living creatures, but among universes, each striving in some way to reproduce, create, and endure. These are profound and speculative ideas, echoes rather than answers, glimpses rather than explanations. We are left with an open universe, both literally and figuratively, a cosmos whose fate may be endless silence or fresh dawns beyond our comprehension. With the evaporation of the final black hole, with every bit of matter and every echo of light dispersed and faded, the universe arrives at a place Einstein and poets alike dreamed of: perfect calm, total equilibrium. Nothing happens, and it keeps not happening, forever. Time becomes meaningless, forever. For the first time in its existence, the universe is both permanent and unchanging. Entropy, having always advanced, now reaches its zenith and ceases to increase, because the cosmos cannot get any more disordered. Nothing remains to happen. The last story has been told. Every last echo has faded. And yet, perhaps, this is not a cause for sadness, but a final invitation to wonder. Everything has its wonders, even darkness and silence. In our brief presence in the cosmos, we learned, we strove, we dreamed. We peered bravely into unfathomable reaches and found our place among the stars, our footprint in the deep sand of cosmic time. So, as we close the book on this story, at least as far as science and imagination can take us, we are left with a kind of cosmic contentment. The universe, at peace, becomes a monument to all that ever was, all that ever could be. Everything has its wonders, even darkness and silence, and I learn, whatever state I may be in, therein to be content. The end, then, is neither a triumph nor a tragedy. It is the last breath of a cosmos that forever invites us to contemplate, to marvel, and to be. The journey, as always, is its own reward. Thank you for joining us at the Sleep Lab on this astonishing journey across eons, beyond imagination, and into the final silence of time. If you found awe in the endless future, subscribe to our channel, share it with fellow thinkers, and remember, wonder never ends, even when time itself does.